Okay, so what do we want to show? We want to show that the set of positive definite matrices is open in the set of all n by n symmetric matrices. Right? So that's a vector space of dimension n into n plus 1 by 2. And we want to show that this subset is an open set in this. Right? So to do that, what we wanted to show was, if we want to show that this is open, then what we should show is that no matter which point we choose in the set, we can construct an open ball around it, which is still contained in this set. Right? So what we want to show, so this would be true if we can show that for any positive definite A, we can look at a ball of sufficiently small radius around A, which is fully contained in this set. Epsilon, which is much smaller than 1. Doesn't matter how small epsilon is, as long as I can somehow construct a ball of sufficiently small radius centered at A and contained in S. Then I'm done. Right? So what is an open set? It's a set where every point is an interior point. So no matter which point I pick, if I pick any point within this set, I can construct a ball of small radius which still lies fully inside the set. So I can go closer and closer to the boundary, but I'm never going to hit the boundary. So I can always, there is some more distance to traverse through before you hit whatever boundary, right? You're still inside the set. Now, what is a ball of radius epsilon in this case? That's another symmetric matrix of sufficiently small norm, correct? And that's easy to show, right? So you take any matrix B of sufficiently small norm, and what you want to look at is A plus B. So is A plus B also a positive definite matrix for any B with norm that is sufficiently small, right? And this is something that we showed in the last class, right? Just by looking at the maximum and the minimum eigenvalues of A, B, and A plus B, we can show that A plus B, as long as the eigenvalues of B are sufficiently small, they're all close to 0, A plus B is still going to be a positive definite matrix, right? And that shows that this is an open set. Right? Is that okay? Any other questions? Okay, so in the last couple of classes, we looked at these objects called proper cones, right? Recall that a cone is proper if, of course, it's a cone and it satisfies the following properties. It's closed, it is convex, it's a solid cone, that is, it has a non-empty interior, and it is pointed. And two examples of proper cones that we looked at was the non-negative orthant, that's a proper cone, and also the set of positive definite matrices, positive semi-definite matrices, right? And using proper cones, we could define these generalized inequalities. So component-wise inequality is one such generalized inequality, which is constructed using the non-negative orthant as the proper cone. But using positive semi-definite matrices, you can also construct other generalized inequalities. So no matter which proper cone you pick, that corresponds to some generalized inequality, right? So in today's class, we look at another class of inequalities, but generated by a different cone. So given a cone, we'll define something called a dual cone, and using those, we get what are called dual generalized inequalities. Now, the application of this will not be immediate. You won't see it right away. But later on, when we define the dual of a convex optimization problem, we'll make use of these dual generalized inequalities. But we'll see some geometric interpretation of these dual generalized inequalities anyway. So let's get on to it. So given a cone, so if K is a cone, need not be proper, it could be an arbitrary cone. The dual of this cone is defined as follows. So I'll denote this by K star, and it's basically the set of all points X in Rn such that X transpose Y is greater than or equal to 0 for all Y in K. Okay. So in some sense, it's the set of all points in Rn which have a positive inner product with Y. It's sort of have a positive correlation with Y, if you can think of it that way.
So the dual cone will always contain a cone.
Let's see, not necessarily. Again, this has to hold for all Y in K, right? Not just for some Y. All right, so let's see some examples of dual cones. So let's take our favorite example, the non-negative octant. Right, so that's K. What would be the set? What would be the dual cone? Okay, someone says third quadrant, someone says K, the first quadrant. Okay, the zero vector. So basically the dual cone of the cone K would be the set of all points which have non-negative inner product with every element in K. Yeah?
R minus 0.
R minus 0. Okay. It has to have positive non-negative inner product with every element in K star should have a non-negative inner product with every element in K. Okay, so let's pick any point in any other quadrant, okay, the third quadrant, would this vector have a positive inner product with any element in K? No, right? The inner product would be negative. Let's take a point in the second quadrant. Would this vector has positive inner product with some elements in K, but does it have positive inner product with all elements in K? No, right? So basically it would have positive inner product if the angle between the vectors would be acute, right? So what about a point in the fourth quadrant? No, right? So no point in the fourth quadrant can belong to the dual cone, right? What about any vector in the first quadrant itself? It would, right? So every element in the first quadrant has a positive inner product with every other element in the first quadrant, or at least a non-negative inner product with every element in the first quadrant. Right? So this is an example where K star is equal to K. So let's take an even simpler cone. Suppose that the cone is just a ray. So you fix a vector x, and you look at the set of all points alpha x, alpha greater than or equal to 0. Maybe x is in the first quadrant. Okay, so that's your cone. This is your K. And now you want to find the dual of this particular cone. What would that be?
Of all cones, always that to the perpendicular.
Correct. So basically everything in this region, so where this is a right angle, everything here would belong to K star. Yeah, correct. Also on this side. So what is this object? Basically the half space. All right, the half space corresponding to defined by the hyperplane, which is normal to this vector x. And what is this equal to mathematically?
Minus 1
Exactly. So it's set of all y such that x transpose y is greater than or equal to 0. So it's a set of all points which have positive, non-negative inner product with x.
Example 1.
Yes.
What is the fourth point?
You take the fourth quadrant. Does it have a non-negative inner product with, what would be the inner product of any element in the fourth quadrant with any element in the first quadrant.
Fourth quadrant within all elements within that.
No, take any vector in the fourth quadrant. Okay, what would be the inner product with any element in the first quadrant?
That will be negative.
It will be negative, right? So that can't be in the dual cone because it has to have positive inner product.
But all will be positive with all elements within the fourth quadrant. Then
Correct. So if K is the fourth quadrant, if K is equal to the fourth quadrant, then K star would also be equal to the fourth quadrant. But if I take K to be the first quadrant, then K star would also be equal to the first quadrant. So in fact, it doesn't matter which quadrant you pick, right? No matter which quadrant K you pick, K star is always going to be equal to K. So it's true not just for the non-negative orthant, but any orthant for that. K star will be equal to K. Right? And this happens in some sense because the cone that you pick is kind of rectangular. The boundaries are orthogonal to each other. That's geometrically speaking. Okay, now let's take the following set. So let K be some K dimensional subspace of R. K can be anything. So is a subspace a cone?
Yes.
It is, right? Because it's closed under all linear combinations. So it's convex, it's also a cone. Okay. What would be the dual cone?
Orthogonal.
So,
except the dimensional orthogonality.
sorry?
Everything that's not orthogonal.
Everything that is not orthogonal to
That's the
K?
definition.
No, it can be, right? So this doesn't exclude x transpose y equal to 0. It only excludes the set of all points for which x transpose y is less than 0.
Yeah,
So in this case, it will be Rn.
Yeah. Sorry?
It will be R. It will be Rn.
Rn?
As K and then everything that is perpendicular to K.
It has K and then everything that is perpendicular to K. Okay. Would it have K? It won't have K. Why? So take any vector x in K and a vector y in K star. Okay. So if x transpose y is greater than or equal to 0, right? If x is in K, then minus x is also in K, right? But then minus x transpose y would be less than or equal to 0. So if you want to find a vector y which has non-negative inner product with some element in x, then what needs to happen? Can it have a strictly positive inner product with any element in K? So you pick an x in K, pick any y in K star. Okay. So if x transpose y is strictly greater than 0, right, then you can find another point minus x for which minus x transpose y is strictly less than 0. So y cannot be in K star, right? Because it's not, it doesn't satisfy the property of an element in the dual cone. So what can happen? The only possibility is that X transpose Y equal to 0 for all Y in K star. So if K is a vector space, then the dual cone can only contain points which are orthogonal to this space. And that is precisely the dual space. All right. So now let's say that K is the positive semi-definite cone. So it's a set of all positive semi-definite matrices, and we want to know what the dual cone is. So again, in this case, the inner product of two matrices A and B is I comma j, Aij, Bij, but this is also equal to the trace of A transpose B or B transpose A. Okay, so I claim that K star is also equal to K. Okay, and why is this true? So let's pick any matrix A in K star. Firstly, I want to show that this matrix is going to be positive semi-definite. All right. So how do we show that it's positive semi-definite? We want to show that X transpose AX is greater than or equal to 0. Right? This is what we want to show. Why? This is K star, not K. Okay, so what is the trace? Okay, so first, what can you say about the vector X transpose? It's a positive semi-definite matrix, right? And why is that true?
Because it become a norm.
Yeah, so if you take let's say y transpose this times y, then this is simply y transpose x times x transpose y, which is x transpose y the whole square, which is greater than or equal to 0. Right? So x, no matter which x you pick, xx transpose is positive semi-definite. Okay. So if you look at x transpose ax for any a in k star, I claim that this is equal to the trace of x transpose times a.
So cyclic.
Yeah,
Trace can be cyclically.
correct. So the trace of a times b is, yeah, you can, a times b times c is the same as the trace of c times a times b. Right? Or if you're still not convinced, you can easily get a closed form expression for this particular quantity. So get a closed form expression for x transpose ax, the ijth entry of x sorry, you can write it as a sum overall ij of a bunch of terms, and you can show that that is equal to this particular quantity. Okay, but what is this? We know that this has to be greater than or equal to 0 because xx transpose is positive semi-definite and a is in k star. So are we done? Yeah. So we also need to show that every positive semi-definite matrix is also in K star. Right? Or let's consider any positive semi-definite matrices A and B. Okay, what we want to show is that the trace of A transpose B is always greater than or equal to 0. Now, the way to prove this is that you can write A in terms of its spectral decomposition. So you can write A as summation I equal to 1 to n lambda I qi transpose, where the lambda i's are the eigenvalues and the q's are basically the eigenvectors. Now, if you look at the trace of A transpose B, or maybe B transpose A, and write A transpose. What will this be equal to? I've just expanded A in terms of summation I equal to 1 to n lambda I qi transpose. But what can you say about this quantity? So what is trace of A plus B equal to? Trace of A plus trace of B. So you can say that this is summation I equal to 1 to n trace of lambda I qi transpose B. But what is trace of some constant times a matrix? Constant times the trace of the matrix. So this is equal to summation I equal to 1 to n lambda I trace of qi transpose times B. We can again rearrange this. I equal to 1 to n lambda I times the trace of qi b qi transpose bq, which is just qi transpose bq. But what do we know about this? This is greater than or equal to 0. And what do we know about the lambda i's? They're also greater than or equal to 0 because they're the eigenvalues of A, which is positive semi-definite. So trace of A transpose B is also greater than or equal to 0 as long as A and B are positive semi-definite. So if K is positive semi-definite, then it is in K star. And if a matrix is in K star, then it must be positive semi-definite. So K star is equal to K. All right. So what properties do the dual cones satisfy? Right. So one property is that K star is always going to be closed and convex. So let's reword the closed bit first. Why will it be convex?
You have to separate phone like for writings. One is positive, other is not positive, and middle part should also be positive.
Yeah. So if I take any x1 and x2 which are in K star, then I know that x1 transpose y is greater than or equal to 0 for all y in K. x2 transpose y is also greater than or equal to 0 for all y in K. But what is alpha x1 plus 1 minus alpha x2? What will be the inner product of this with y? This will also be greater than or equal to 0. Now suppose I have two cones, K1, which is a subset of K2. What can you say about K1 star and K2 star? Is one of them going to be contained in the other?
Okay, that's contained.
K2 star is going to be contained in K1 star. So let's take any, okay, so let's look at K2 star. Okay. What can you say about this? So X transpose Y is greater than or equal to 0 for all Y in K2. So if I take any Z in K1, what happens? What would X transpose Z be? Greater than or equal to 0 because Z is also in K2. If Z is in K1, then Z is also in K2. So X is also in K1. So you pick any X in K2, K2 star, this X will also lie in K1 star. But the reverse need not be true. So just as an example, go back to this. So if K1 is, let's say, the non-negative quadrant, the first quadrant, and K2 is just this ray in the first quadrant. So K2 lies in K1, but what can you say about K2 star and K1 star? So this is my K1, this is my K2, and K2 is contained in K1 in this case. What can you say about K2 star and K1 star? So K2 star is this entire half space, whereas K1 star is only the first quadrant. The first quadrant is fully contained in the half space. Right, so K1 star is contained in K2 star. So if containment goes a certain way for the original cones, then the dual, for the duals, the containment is the opposite way. Okay. So if K has non-empty interior, then K star is going to be pointed. So let's try to prove the contrapositive, which is if K star is not pointed, then it cannot have a non-empty interior. So suppose K star is not pointed. What does this mean? It's a cone. It can be a cone, right? But it need not be pointed. What does it mean for it to be pointed? Yeah. So it means that there's some non-zero vector for which the negative is also in the cone. Right? So there's some non-zero vector x and minus x, which also belongs to K star. Okay, so what can you say about y? So take any y in K. Yeah? Yeah, so every vector in K should be orthogonal to the vector x. Right, because y transpose x should be greater than or equal to 0. Y transpose minus x should also be greater than or equal to 0. That can only happen if y transpose x is equal to 0. So what can you say about K? What is the dimension of K?
Not full dimension.
Yeah, so if you look at the affine dimension of K, this is less than or equal to n minus 1. Whatever it is, it should, the entire K should lie in a subspace of dimension n minus 1, right? Because every vector in K should be orthogonal to the vector x. Right? And the set of all vectors which are orthogonal to one particular vector, they form a subspace of dimension n minus 1. So this means it's not an n-dimensional object. It's at most an n minus 1 dimensional object. So it cannot have a non-empty interior. You can't pack in a ball of radius, of any positive radius inside K. Now, what about the reverse? If K is pointed, then what can you say about the interior of K star? It turns out that K star has non-empty interior. Yeah, yeah, it's going to be very similar to this, but how do you argue?
Yeah, there should be an x and minus x.
Okay. So suppose that K star does not have a non-empty interior. Okay, so it's not a full n-dimensional object. It's at most an n-1 dimensional object.
Then like derivate is one vector or the
Correct. So it's a it lies in a subspace of dimension less than or equal to n-1, which means that there should be at least one vector which is orthogonal to this, because this lies in some subspace. And what can you say about the dual space? What would be the dimension of the dual space? At least one, because you can think of this as the column space of some particular matrix. So the null space has dimension at least one. So there's at least one vector which is one non-zero vector which is orthogonal to every vector in K star. So K star has a non-empty interior. It's a cone, right? So that can happen only if K star lies in a vector space of dimension less than or equal to. So firstly, the affine dimension should be less than or equal to n-1. Correct? Yes. If you, yeah. If you have an empty interior, yeah. Okay. So can you think of a cone which has an empty interior, but is not contained in a vector space of dimension less than or equal to n-1? Sure. Think about it.
okay. Take two rays
Yes.
in 2D space.
Yes.
What is the
If I take two rays in 2D space,
that's an empty interior.
that has an empty interior, yes.
But what is it?
The dimension would be 2. Okay. So I want this to be,
This has to be convex.
sorry, yeah. So K star should be convex. That's something that I missed. Sorry, K has to be convex. If K is convex and pointed, it's a convex cone.
Okay, star is always convex.
Sorry?
Yes, star is always convex.
K star is always convex.
So this K also has to be convex to the previous one also.
So in this case, if it has a non-empty interior, not really, right? Because the only assumption we made was that it has a non-empty. Well, K star, if K star is not pointed, then K cannot have an empty interior. Which one? Whatever, K star has to be convex.
But K star is always convex.
Which?
Like
Okay.
that was the first problem.
That's true. K star is always convex. Correct. So then this requirement is not required. Which? K star is always convex, but the non-empty interior is only for K star. So you don't need this. Right. So if K star is convex, it's a convex cone, and it has a non-empty interior, then it will lie in a vector space of dimension less than or equal to n. So then you can find a y which is orthogonal to every vector in K star, and this implies that y is in K and K is not point. So in summary, if K is a proper cone, then what can you say about K star? So K is closed and convex. Well, K star is always closed and convex. And if K is a proper cone, then it has a non-empty interior and it is pointed. So K star will be pointed and have a non-empty interior. So K star is also a proper cone. Yes. Well, it's a little subtle. So the dual of the dual will be the closure of the convex hull, because the dual of the dual will be a closed and convex cone, but the original cone may not be convex or closed. So this implies that yes, correct. Okay, so that's true. So let's think. I think. Yes, that's true. Okay, that's a good point. I will think about it, come back by the next class. So here I have claimed that there exists a y which is orthogonal to every vector in K star. But so this implies that y is in the dual of K star, right? But it doesn't necessarily imply that y is in K, because the dual of the dual need not be equal to K itself, particularly if K is not closed or convex.
But K will always be contained in the. Or
K is contained in the dual of the dual, yes. But potentially this vector y belongs to the dual of K star, but not in K.
You take some random y in K, that will also give y transpose x equal to 0.
Why? Not necessarily, right? So we've shown the existence of some y which is orthogonal to every vector in K star. Right? But of course, if K is also convex and closed, then it's fine. Right? But if K is not convex, for example, then this may not hold. Right? So for example, I could take just two rays. The dual of this is going to be, it's going to look something like this. Right? So the set of all vectors to the right of the blue lines. But the dual of this blue cone will in fact be the entire region that is between these two rays.
This is process called the properization of a cone.
Sorry?
This is process called the properization of a cone.
I don't know what it is called, but it's just equal to the convex hull of the original cone. That's it.
so the dual of the dual is always equal to the convex of the original set.
Yes. It's equal to the convex closure of the original set. The original cone may not be convex. It need not be closed. Okay, so if K is a proper cone, then K star is a proper cone. So if we were able to define a generalized inequality using the proper cone, then it means that you can also define a generalized inequality using K star. Right? And what do the inequalities correspond to? Right? So recall that if you have two vectors and some cone K, then X is less than or equal to Y. This generalized inequality is true. We say that X is less than or equal to Y if and only if Y minus X is in K. Right? And what does Y greater than or equal to 0 imply? Yeah, so Y belongs to K. That's another way of saying that Y belongs to K. Right? So if X is less than or equal to Y, and let's take a vector lambda which is in K star. Right? This is the same as saying lambda is greater than or equal to 0 in K star. what can you say about lambda transpose X and lambda transpose Y?
less than equal to.
So X is less than or equal to Y according to this generalized inequality. And lambda is an element of K star. Then what is lambda transpose X compared to lambda transpose Y? It's going to be less than or equal to lambda transpose Y. And why is that true?
Y minus X becomes
Yes, so Y minus X belongs to K, right? That's just by the definition of this generalized inequality. And since lambda is in K star, it should be the case that Y minus X or lambda transpose Y minus X is greater than or equal to 0, which can only happen if lambda transpose Y is greater than or equal to lambda transpose X. So let's take a general set S. So let's suppose any set, or maybe let me call this A. Now on Rn, I define a generalized inequality using some cone K. Right? Suppose this set A has a minimum. So you could think of it in the following way. Suppose that the set S looks something like this. This is my S. This is my set A. So which one would be the minimum? If I used, say, the component-wise inequality, is there a minimum? There is no. Right? So now, is there a minimum? And which point is the minimum? The new vertex that I got. So this would be the minimum of A. So this is the minimum of A under the generalized inequality K, right? So this, you can also write this as the solution to a linear program. And that is, well, it's not exactly a linear program, but it's the minimum of a linear functional. So I use this new sort of notation over here. lambda greater than 0 under k star. This simply means that lambda is greater than or equal to 0 under k star, but lambda is not equal to 0. So what does this statement say? It says that suppose I have a generalized inequality, then I can write this and I have an x star which minimizes or is the minimum element in A under the generalized inequality K. Then this x star is basically the minimum of some linear functional taken over x in A. All right, and this holds for any linear function such that lambda, the coefficients come from the dual cone. Okay, and why is this true? It just follows from the previous property. So x star we know is less than or equal to x for all x in A. That's by definition of the minimum. Right? But this implies that lambda transpose x star is less than or equal to lambda transpose x for all x in A. So in other words, x star is the one which minimizes lambda transpose x.
So
Yeah.
can you say that R may not lambda?
Right. Should be the R. And something similar happens for minimal elements as well. Right? So now if the set looks something like this, which would be the set of minimal elements under the component-wise inequality? So it's so the points along this particular edge correspond to the minimal elements. So if you take any lambda in k star, right, and not equal to 0, and let us say that x star is minimizes lambda transpose x. Then x is minimal. So suppose that x star is not a minimal point. Then what can you say? So you can find an x in A for which x star is greater than or equal to x, right? But this would imply that lambda transpose x star is greater than or equal to lambda transpose x, and then x star would not be the minimizer of lambda transpose x. Okay, since we're talking about generalized inequalities, I'd like to give some more intuition for this component-wise inequality, right? And what it means for an element to be minimal, right? So, yeah, so minimal. So we know what it means geometrically, right? At least in 2D, a point is minimal if it basically corresponds to an edge in some sense, right? But there's also an optimization interpretation to a minimal element, and that is the following. So let's look at the component-wise inequality. Right? And you're given a particular set. This some set A could be convex, need not be convex, doesn't matter for now. And we want to interpret a minimal element of this particular set. Okay. So one way to think about any element of this set is kind of, you have multiple, let's say, resources that can be used. Okay, so any x in A can be thought of as a resource vector. Right? Which is the amount of resources that you allocate to different items. So for example, let's say I have x1, x2, x3, and say you're trying to invest in a bunch of portfolios, then x1 is the amount you would invest in, let's say, item 1, x2 is the amount that you would invest in item 2, and x3 would be the amount that you want to invest in item 3. Okay? And A is whatever it defines your constraints, which it basically tells you how much you can invest in something. Okay, maybe that's maybe A corresponds to, let's say that if the rewards have to be a certain amount, then the vector x should lie in A. So in a sense, what would a minimal element correspond to? Suppose you're operating at some point which is minimal. So if it is minimal, then I have x1 star, x2 star, and x3 star. So firstly, it means that I can't find any element in A which is strictly less than this particular, right? Which is less than or equal to this particular vector. But there's another way to interpret this, particularly in the case where it's a component-wise inequality. It means that if I keep everything else fixed, right? If I keep all the other coordinates fixed and try to see if I can, reduce the amount that I would have to allocate to the ith resource, then it's not possible to do that, right? So if I keep x1 star and x3 star fixed and try to vary x2 so that I'm still lying inside A, can I find a better allocation? So you look at x1 star, x3 star, x2 in A, right? You're keeping the resources allocated to the other items fixed, and you want to choose the best resource for the second item, just the second item. Then can you do any better than x1 star, x2 star, x3 star? You can't, right? Because if you could, then that would violate the property that x star is a minimal point. So particularly in the case where you're looking at the component-wise inequality, a minimal element is also called a Pareto optimal point. So the sort of economics interpretation of this is that it's not possible to improve one person's well-being without causing a detriment to someone else's well-being.